This video, episode 13 of the Mastering AI ML series, will visually explain decision trees and random forests. Decision trees are easy to understand, but can overfit training data. Understanding how random forests fix this is crucial in applied machine learning. This program is brought to you by the Series of Thoughts team and Technovative AI. We will cover 8 key ideas, starting with the flowchart analogy and moving on to choosing splits using Gini, impurity, and information gain. We'll then look at overfitting and pruning, the bias-variance tradeoff, and how random forests work. Finally, we'll explore feature importance and gradient boosting. A decision tree's core intuition is a flowchart of yes-no questions about features. At each node, an algorithm picks a feature and a threshold. This leads down to a leaf node that provides the prediction. It's a simple branching logic. The root node is the most informative split. Branch nodes continually split subsets of data. Leaf nodes hold the final class label or regression value. Depth is the number of levels below the root. Using the Telco Churn dataset, the root split asks if tenure is less than 12 months. This is the strongest signal for churn. The left branch asks about month-to-month contracts. The right branch asks about monthly charges greater than $70. The tree chooses a split by trying every feature and threshold to produce the purest child nodes. This means nodes should be as homogeneous as possible. Gini, impurity, and information gain are the 2 key metrics used in practice. Gini impurity drops from 0.5 for a completely mixed node to 0 for a pure node. The curve peaks at 0.5 for a 50-50 mix. The tree's job is to push both child nodes towards 0 impurity at every split. Unconstrained decision trees will overfit. They keep splitting until every training sample is perfectly classified, achieving 100% training accuracy. However, they memorize noise and fail on new data, resulting in poor test accuracy. This is overfitting in its purest form. A fully grown tree has a jagged decision boundary, tracing every training point, leading to overfitting. A pruned tree with limited depth or minimum samples has a smooth, generalized boundary that captures real patterns and performs better on unseen data. Pruning is the art of controlling tree growth before it memorizes noise. Key levers include maximum depth, minimum samples to split a node, minimum samples in a leaf, and cost complexity pruning via CCP alpha. Simple settings like max depth 4 and minimum leaf samples 5 are good starting points. The bias-variance tradeoff is a fundamental concept in machine learning. The classic U-shape shows that too little complexity leads to high bias and underfitting, while too much complexity leads to high variance and overfitting. The goal of hyperparameter tuning is to find the sweet spot in the middle. High bias, or underfitting, means the model is too simple and consistently wrong. High variance, or overfitting, means the model is too complex, unstable, and wrong in random directions. The goal is to minimize generalization error, not just training error. Instead of one perfectly tuned tree, what if you built hundreds of imperfect yet different trees and let them vote? Their uncorrelated errors cancel out when averaged. This is the core insight behind random forests, an elegant idea in ML. Random forests use 2 randomness sources to decorrelate trees. Bagging trains each tree on a different bootstrap sample. Feature randomness considers only a random subset of features at each node split, forcing diversity among the trees. Bootstrap sampling draws samples with replacement, creating separate datasets for each tree. This trains individual deep decision trees. The predictions are then aggregated by majority vote or mean for regression. The out-of-bag samples serve as a built-in validation set. Averaging reduces variance. The math shows that when trees are uncorrelated, variance reduces by a factor of n, the number of trees. The intuition is like the wisdom of crowds. Individual errors cancel out, creating a calibrated consensus. Comparing the 2 models, decision trees are highly interpretable but have a high risk of overfitting. Random forests are black box ensembles, but offer low overfitting risk and high stability due to variance cancellation. Both handle mixed data types and do not require feature scaling. A key output of a random forest is the feature importance ranking. This measures the total reduction in impurity across all splits, averaged over all trees. This ranks which features contributed most directly to reducing uncertainty in the prediction. For the churn dataset, the feature importance chart confirms that tenure and monthly charges dominate. Unlike a single greedy decision tree, this averaged, robust estimate across 500 trees provides a much more trustworthy view of predictive power. When reading feature importance, beware of biases. Correlated features dilute each other's scores. High cardinality features can get artificially inflated. For a bias-free alternative, consider using permutation importance for validation alongside the standard impurity-based method. Key hyperparameters include N estimators, the number of trees, max features, controlling tree diversity, and max depth and min samples leaf, controlling individual tree growth. In practice, N estimators and max features offer the quickest wins for tuning. This code demonstrates the sklearn pipeline, training both a pruned decision tree and a random forest. Notice how the random forest uses a high number of estimators, uses all CPU cores with n jobs equals -1, and leverages out-of-bag scoring for free validation. The decision tree's superpower is explainability. In regulated industries like banking or healthcare, an explainable model is often mandatory. A pruned tree can be audited and used as a direct basis for a decision, a property random forests sacrifice for accuracy. Use cases demanding explainability include credit scoring, medical diagnosis, and legal decisions. When accuracy is paramount, such as in fraud detection, recommendation engines, or marketing, random forests typically win. Random forests excel on tabular or structured data with mixed features. They are robust to noisy data and outliers because splits depend only on rank, not magnitude. They are excellent for rapid baseline prototyping, requiring minimal pre-processing. Trees struggle with unstructured data, like image or text, which needs specialized architectures. They cannot extrapolate beyond the training range in regression. They also perform poorly on extremely high-dimensional sparse data and when precisely calibrated probabilities are needed. Looking ahead, gradient boosting builds trees sequentially, where each tree corrects the errors of the previous one. This creates a dramatically powerful learner, dominating Kaggle competitions. We'll explore XGBoost, LightGBM, and CatBoost later. Bagging and boosting tackle different problems. Bagging, used by random forests, reduces high variance in unstable models. Boosting reduces high bias by fixing mistakes sequentially. Boosting often achieves lower error, but is harder to tune and more prone to overfitting noisy data. Start with logistic regression for linear, regulated, or high interpretability needs. Next, try a random forest for tabular data and a strong baseline. Then escalate to gradient boosting for maximum tabular accuracy. Only reach for neural networks last, primarily for unstructured data. You should now understand recursive splitting, impurity metrics like Gini and information gain, the bias-variance tradeoff, and how random forests use bagging and feature randomness to reduce variance. Finally, you can critically interpret feature importance. Here is a quick reference for the key formulas covered in this video. These include Gini impurity, entropy, and information gain, which are essential for making splits in decision trees. Avoid common mistakes. Always set a random state for reproducibility. Use enough trees, preferably 300 to 500, to ensure stable results. Validate impurity-based feature importance with other methods, and always handle class imbalance. In summary, decision trees are brilliant but brittle. They require pruning. Random forests fix variance by introducing diversity. For structured tabular data, random forests are an essential production-ready baseline model. Next up is episode 14,
where we cover unsupervised learning and clustering. We'll explore how algorithms find structure in data and look at methods like k-means and dbScan without relying on pre-existing labels. For further learning, check out the original Brayman paper on random forests and chapters in The Elements of Statistical Learning. Practice with scikit-learn, dtreeviz, and the SHAP library. The Telco Churn dataset is available on Kaggle.